Next Monday, and there's a final next Thursday. So just giving you a heads up. The final, the one thing that I wanted to mention, the final is at 1:30, 1 o'clock, I think. Does anyone remember? I think it's at 1 o'clock on Thursday. It's for 2 hours, and the other announcement was your project reports are due on the last day of the exam period, whatever that day is, about a week after the final, basically. So that will give you some time to clean up stuff and run some experiments. You should have gotten back some feedback about your status by now. If you haven't, send me an email. Most of you seem to be doing interesting things. The one consistent worry that I have for many people who have to run experiments is it may take time. As long as you think it will probably take a couple of days more. So just give yourself enough time to run experiments, and so that you exhaust, or at least you don't have to exhaust, but at least try out an interestingly large set of variants for your algorithms, features, parameters, hyperparameters, or anything. Questions? Did you look up the one? It's 1 o'clock, so it's
in here.
In here, yes. And a couple of you emailed me saying, I don't know if you're in the class, but emailed me saying there's some conflict. There's another final happening at the same time. If that still holds, then send me an email. I'll try to work things out.
So what should be updated for the final report due date?
I'll do that today. Yeah.
So is Thursday the 6th?
30th. Wait, for what?
For the final.
The final is 30th. Next Thursday. Next Thursday. Yes. And huh?
That's it.
Yeah, you have 10 days, so it's okay. And the report is due a week after that.
Do we have class Wednesday, or is Monday the last day?
Monday is the last day. Wednesday is reading day. So Monday is the last day. My plan is to spend at least half of Monday talking about practical aspects of learning. I mean, all these algorithms and theorems are nice, but it's good to also know what to do with them. So that will be the goal for Monday. This week we are going to continue looking at unsupervised learning and some interesting tidbits about features, because we've not really spoken much about features in the class. In particular, I'll primarily be talking about a little bit of clustering and dimensionality reduction in the next lecture. Today the goal is to wrap up EM and work through 2 examples. Questions? Let's continue where we left off. One other sort of announcement is I had to change the slides quite a bit. Remember, I told you that there was a mistake in one of the slides, in a little bit of the math, so I ended up changing it, and while doing that I realized that there might be a somewhat easier way of walking through the same material. Not much different, but just a subtly different but probably more intuitive way to understand this. So I'm going to walk through that. We were in this we were playing this game with 3 coins. We had 3 coins, coins 0, 1 and 2. And the first scenario was when we have all the biases of the coins, the alpha, p and q, and we are given a string like this, h, 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 t, and we are told that it either comes from coin 1 or coin 2, I don't know which one. And you're asked which one is it, and you do, and the way to answer that is to do maximum likely or maximum a posteriori. So to answer which coin generated the data, if you knew all the parameters, you can just estimate probability of y. I'm going to use y for the identity of the coin that generated the data, given x. equals, say, something like this, and your parameters. And we know how to do this because each one of these is independent. You can just use the standard maximum likelihood estimation, or maximum likelihood prediction, in fact. That's scenario 0 or scenario 1. Scenario 2 is when you're given fully labeled data. So now the game is first you toss coin 0. If coin 0 gives you heads, then you pick up coin 1 and toss it 4 times. If coin 0 gives you tails, you pick up coin 2 and toss it 4 times. And so you're given data that looks like coin 0 is heads, and then you get 0 is tails, and something like this. So in some sense, the first one, the letter in blue, is y, and this is y and this is x. And if you are given fully labeled data of this kind, we know how to estimate alpha, p and q. Basically it's naive Bayes. So you just count and you take averages and you're done. So that part is easy. The difficult bit is, this is x. When you generate the data this way, but you're not told this data. You're only given strings of this kind, just the value of 1 or 2, but not the identity of the coin that generated it. So the question is, how do you estimate these probabilities? And I mentioned in the last lecture that in general this problem is really not solvable. There's no analytical solution. We need an algorithmic solution. When I say analytical solution, I mean there's no way of just deriving the probabilities on paper just like we did for naive Bayes. We need to use an algorithm to actually estimate these values. So just to summarize what we know, if we know what the coin biases are, we can compute the probability that a particular observation, an observation is a string of 4 characters, comes from a certain coin. We can compute probability of the missing variable given the observation and the coin tosses. Conversely, if you knew which data points came from which coin, you can calculate all the probabilities just by counting. So these are the 2 pieces of information we have and we know how to do. And the goal is to build an algorithm that can use this as a building block to compute the whole probabilities, all the probabilities. And the general flavor of the algorithm looks like this. You first take a guess that for every observation you guess whether it comes from coin 1 or 2. You're probably wrong, but you just take a guess. And then you keep iterating. You first, instead of taking a guess, you can also estimate the probabilities of, you take a guess to all these probabilities, alpha, p and q, and then use these probabilities. Now you have the probabilities and you have the observations, you can compute which coin generated it. This was scenario 1. Yeah, this was scenario 1. You have the observations and you want to compute which coin generated it. It's possible that these labels might be fractional. But pretend that the labels are not fractional. Then you have fully labeled data. You have for every observation, you have your best guess as to where this comes from. So you have fully labeled data and you know how to compute the probabilities, all the next iteration of alpha, p and q. And you keep iterating these 2 steps. So now you know these alpha, p and q. You go back and estimate which coin generated this. And now you have fully labeled data. You go back and we compute the probabilities. This is the flavor of EM. Okay? And the good news is that this will converge to a local maximum of the overall likelihood. But the fact that this works is entirely should not be obvious. First of all, is this algorithm clear? Is this strategy for learning clear. Effectively, you have some missing labels. You just hallucinate some parameters and make a best effort guess at filling in that rest of the data. Now you've filled up the data, you have fully labeled data. You use whatever standard learning algorithm you have to re-estimate the parameters. Now you have parameters. Re-estimate the labels and keep going back and forth. That's the general flavor of EM. Questions? Yes?
So is there a theory for this?
There's a lot of theory for this, and I'll be presenting some amount of theory, but not in great depth. So, good question. That's the rest of the class. So, we are in the world of maximum likelihood estimation. So, what we want is we want to maximize the likelihood, or effectively the log likelihood of your training set given your parameters. But your training set only consists of examples. So in this case, for example, your parameters are alpha pq. Your training set consists of strings of this kind, just the black stuff, not the blue stuff. And I already mentioned this notation. I'm going to use the value of the coin toss for the value of coin 0 is the random variable y, and everything else is random variable x. Then it fits in this intuition that we've had, or in this notation that we've had for the entire semester, where x is the input and y is the label. So what we want is to maximize the log likelihood of your training set given the parameters, which is simply the sum over log likelihoods for every example. Why? Because every example is independent. And we've seen this applied many times so far. But the full example, the model that we have, P of x, tells you our probability model says P of x, y, given alpha p q, it looks like this. If y equals heads, it means that, or if y is heads, then you use coin 1. So did I say coin 1 or 2? Coin 1. So that means you use p. So you have, and let's say x consists of k and consists of k heads and 4 minus k tails, because there are only 4 things in each sequence. So this becomes alpha times p power k and when y is tails, you toss tails, so it's 1 minus alpha times q power k . Okay, so what we know is to write down this is our model actually. Our model says this is the probability of a full joint assignment of x, y given your parameters. But the log likelihood term here has probability of just example of the observation. It only talks about P of x given theta is a set of all parameters, and this is notation that you'll see very often in these models. So it only tells us our model has something to say about P of xy. Our log likelihood is only about P of x. How do you get P of x using that?
Sum out y.
Sorry?
Sum out y.
Sum out y, exactly. So you marginalize the hidden variables, and so you get exactly that, sum over y, P of xy, and we know how to write that. Okay, yes?
I think probably the y should be on the other side of the bar, right?
No, this is a joint model. This is a generative model,
Okay.
not a discriminative model. In fact, even in a discriminative model, y will not be on the other side of the
Okay.
line. This is a joint, so that's important. In the assumption that we are making is that we are in the world of joint models. Logistic regression, for example, talks about p of y given x. Here our model tells us about p of x comma y, which is why we are able to sum out the y to get p of x. So effectively what we want to maximize is this expression here, sum over all I, sum over all y, no, log of sum over all y. Now it turns out that maximizing this kind of a function is not a very pleasant one. It's not a pleasant thing because it's not, it's computationally difficult. So this is the log likelihood we want to maximize, but sum inside log is a bad function, especially when the number of y's can be large. I mean, here we have binary, but it's possible that the y's can be more complex. You might have to sum over all graphs, for example. So this becomes computationally difficult. Mathematically, it's not convex. So what do? So that's the point of EM. The EM algorithm wants to summarize this the log likelihood of the data and arrives at a proxy, and which is easier to optimize. And this proxy ends up, optimizing this proxy ends up getting us to a local maximum of this function, which is about the best you can do if your function is not convex or concave in this case. So we want to maximize this function, and at the heart of this is a neat trick. And I'm going to introduce the trick without motivating it, and we'll see why it's interesting in a bit. Suppose you have some probability distribution over the y called Q of y. Q is a distribution only over the y's, and it's completely independent of theta. What I've written there is the Q does not have to be anything. Q can be any function that's not zero, that's valid, but pretend that Q is a probability distribution. Now if Q is a probability distribution, then this summation over y is basically the definition of expectation with respect to this distribution. So expectation of any function with respect to Q is sum over all possible things that the function can take, Q of z, f of z, if Q is the function defined over z. So in some sense, what we have here is an expectation because we have probability and some function. So it's the expectation of that function with respect to that as of now unspecified distribution Q. But let's write it this way and see what happens. So you have log of an expectation of a function. Still I've not, if you think about it, I've done nothing. This is just algebra. There's no, nothing here. Now here's the next step is what makes it interesting. To simplify this, we need to appeal to something called Jensen's inequality. And I mentioned this in the class last week, I'm going to go mention it again. Jensen's inequality is, one way of thinking about it is this is a definition of a convex function. Basically it says if any function that's convex and let's say x is some random variable, f of the expectation is less than or equal to the expectation of f, the function. So if you have a function that's convex and you pick any 2 points, this is a function that's convex. Pick any 2 points, let's say. The definition of convexity says f of lambda x plus 1 minus lambda y. So the definition of convexity. Now, suppose lambda and 1 minus lambda were some distribution. Let's say that lambda is a coin toss, represents the bias of a coin toss. Lambda is a number from 0 to 1, so you can think of this as an expectation, f of expectation with respect to that lambda. Right? And this is the expectation of the function. And this generalizes to Jensen's inequality, and if a function is concave, then the sign just reverses. So what we have is f of e of x is greater than e of f of x. For us, the function that we care about is log of some expectation of this random variable. So log is concave, and the whole function inside the expectation is some random variable. So Jensen's inequality tells us that log of the expectation is greater than or equal to expectation of the log. Now this might seem rather like some boring detail, but this is really what does all the heavy lifting, because log of expectation has a summation inside the log. This gets rid of it. So basically, but what this means is we were here right now, the log likelihood is sum over all points, log of expectation of that function, and just throwing in Jensen's inequality gives us this lower bound. And I'm just rewriting it so that the q term goes to another side. So what we have now finally is the log likelihood of the data is greater than or equal to the sum of expected log likelihood of the full data minus, effectively, that's, if you think about it, that's actually the entropy of Q. That's the plus the entropy of Q, actually. That's the definition of entropy or log. But here's the question, or here's one way to think about it. I care about the log likelihood of the entire data, which is really difficult to optimize. Instead, I have a lower bound. Now, if this lower bound were tight, then maximizing this tight lower bound will take me as high as possible to the peak. So that's our strategy. We want to maximize this lower bound on the log likelihood, with the hope that it takes us to the top of the entire function. And how do you make sure that this lower bound is tight? We have this one unknown still, which is Q. We play with the Q. We play with it till this inequality becomes tight. Questions? How do you know if it's tight? Now, I'll give you two answers there. It turns out one answer is, well, let me just summarize where we are and then get back to your question. What we want is to maximize the log likelihood, and what we instead end up doing is maximize this function of theta and q, which is a lower bound. And the question is, how do you know that this inequality is tight? How do you know that this inequality is tight? The Jensen's inequality is tight when your function is basically a linear function. So what we want is this random variable to look like a constant, and there's some math involved, but it's not terribly hard to show that one way to make the lower bound tight is if you had some current estimate for the probabilities theta. I don't know where it came from, I don't care where it came from. If you have some current estimate for the probabilities, then you set q of y to be the probability of y for each example given your current estimates. And this ends up making the, there's a proof behind this, I'm not going to get into it, but this ends up making the inequality tight. Questions about this intuition, and I'm going to walk through this in a couple of different, for two different models, but questions about the big picture at this point. Yes.
So what do you mean by we have an estimate of theta? Does that mean you sort of have a guess of the parameters?
You guess your parameters. You start with some guess, just a random guess. You hallucinate the parameters and hope it works. So you run with it and you keep optimizing this in an iterative fashion. In fact, that is our algorithm. So the EM algorithm, expectation maximization, which to me is a wonderful name. By the way, this algorithm was defined, it was, I think it's from what is now one of the most highly cited papers in machine learning. It came up in 1977. And this EM is one of those algorithms that you should know. And by that I mean not for your exam or for your class or for your project or homework, but in life it's an algorithm that you should know, because there will be a point when you will come to a situation, if you want to apply machine learning, there will be a point where you do not have labeled data. And pretty much any unsupervised learning algorithm ends up resembling EM. You don't know the labels, but you make a guess. And so you don't know the labels and you want to learn parameters, so you guess the parameters, estimate the labels, and then learn the parameters using the estimated labels and keep iterating. So the EM algorithm looks like this. You initialize your parameters theta naught, and cleverly I have not said how. If you know something about your problem, you should by all means use your knowledge. If not, you just take a random guess and hope it's good. And you iterate until convergence. First, there's the E step, the expectation step, which there are multiple ways of saying this, but effectively it comes down to defining those Qs. You have your current estimate for your parameters, theta t. You use those to find for every data point the distribution over the labels according to your current parameters. So P of y given xi and theta t. So this is your best guess about what the labels should be according to your current model. And then there's the M step. You maximize this proxy function that we come up with, the lower bound for the log likelihood, with respect to parameters. And notice that the only variable in this maximization is the theta. And finally, you keep iterating this step. At this point, you have theta t plus 1. You maximize this function, you get another theta, you go back, they estimate the Q, and iterate. Now, this is not an algorithm in itself, it's a recipe for generating algorithms, because this step, maximization, itself requires some heavy lifting. Sometimes it could. But one thing to notice is this term here, the last term there, is independent of theta. If I'm maximizing this function with respect to theta, I can drop the last one. So effectively, the EM algorithm looks like this. So you estimate the Q using your current parameters for every data point, and you find the next estimate for parameters by maximizing the expected log likelihood of the data given your current parameters. Questions? Yes?
How close does Q actually get to a valid probability distribution?
It should be a valid probability distribution. It's by definition this guy.
Right, I guess my question is there a situation where you have to initialize Q based on your choice of theta naught? We don't have a way to estimate these theta t's based on our parameters.
Say that again. Can you speak up a little?
Maybe I'll ask again.
Okay. So a couple of points about the intuitive, why this is an intuitive thing to do. The E step is asking what's the distribution of the hidden variables using the current set of parameters. And the nth step is using the current distribution over the hidden variables, re-estimate the parameters using the entire data. And keep iterating these two steps, and the math guarantees that you'll get to a local maximum of the true likelihood function, which is pretty cool. Now the other thing is to notice, in terms from the more practical point of view, given theta t, computing q is easy. Why? So, for example, given in this case theta t is this. Given theta t, I can compute p of y given xi. Can I?
This becomes like scenario 1.
It's exactly that. It is scenario 1. But does this relate to the question you had?
Yeah, I think that essentially answers the question.
Okay, good. So, computing, given if you know the parameters, computing the posterior distribution over the labels is easy, because effectively that's what your model gives you. You made an assumption that your joint distribution looks like this, so computing the posterior is easy. The nth step is not that easy. You should either solve it analytically on paper like we did for naive Bayes, or if your maximization, if this whole expression is especially if your model is some nasty function, then you may have to do some approximation there also. And before I get to, okay, so let me just see where we are. One point is that EM will converge to the local maximum, but it's only a local maximum, which means running the same algorithm twice with different initializations could take you to different solutions. So now how do you know what's a good set of parameters? No way of knowing, because there's no labeled data. So how do you know? So remember that in unsupervised learning, when you have no labeled data, you can't break symmetries. So the local maxima are all equally good. The other question is how many iterations do you run this for? The basic algorithm says just run it till convergence. This is the same kind of statement that you see in, for example, stochastic gradient descent for various algorithms. You run it till convergence, but in practice you may want to just run it for 10 steps or 1,000 steps or a certain number of fixed steps. But in this case you can actually keep track of convergence, because you can measure the value of this function and see how much it changes across every iteration. Yes?
So why can't we just max out each of the local maximums? Or
You can do that. In fact, that's a very common thing. You do random restarts and you find the one that's the best one. But the problem is that if your search space is very large, there may be tons and tons of local maxima. You may never exhaust all of them. So, in fact, the random restarts policy is probably one of the most robust ones. You just try 100 things and pick the one that has the best objective value and pick that as the best one. Another point is, this is what I've described as a general schematic for EM. It's far from a complete learning algorithm, because to define the learning algorithm, we need an assumption about the model, like that, and we need to say how the maximization step is done. These are the two things that we need actually. So let's instantiate this algorithm for the 3 coins example to actually see how this works. But before that, questions about EM, about the algorithm, about the general effectively philosophy. Yeah.
Oh, just have a comment. Like from the math point of view, it's like we have a very complex objective function to maximize, maybe involving, like in this case, 3 unknown parameters. It's too hard to optimize simultaneously, but maybe one of them is kind of dependent on the other. So we like pretend we know, for example, 2 of them.
It's
And
not
then
exactly the same,
solve
because
that.
if you think about it, even if you have many parameters, say for example for logistic regression, the number of parameters you had is as many features as you have. But because the objective is convex, you can do gradient descent.
Yeah, that's right. Yeah.
The problem is that log likelihood of the data is not a convex function because there's a sum inside the log.
That's right. So the strategy here used is like maybe we can solve, like if we know 3 of them, we can like solve the 4th one.
Not quite, because the M step gives you all of them. The E step, in some sense, the E step completes the data. You have, and every example is incomplete. The E step effectively completes the data, and the M step uses the completed data to re-estimate all the properties. Once you have complete data, you are in the space of fully supervised learning. This is kind of a hand-wavy argument, and I'll tell you why. And when we look at the actual derivation in the coins or the naive Bayes case, you'll see that this is not too far from the truth. So, just to give you just to make sure that we are all on the same page, where are we? We are in the space of learning when we don't have fully labeled data, and in particular we are playing with the 3 coins. So we looked at scenario 1 and 2, where if you knew the parameters, you can estimate what was the hidden, if you knew the parameters and you saw the observation, the x, you can estimate y. And scenario 2 is if you have complete data, you can learn all the probabilities. And we know how to do that, maximum likelihood works. Scenario 3 is the one that takes us to this direction of EM. If you don't have complete data, meaning you only have the x's, I've erased it, if you only have the x's, can you estimate all the probabilities? And if you notice, nothing in the argument that I presented has anything to do with coins. It's just the algorithm here has no alpha, p, and q. It's basically all of them have been summarized into theta. There's nothing about specifically the model which is completely contained in this box, in this function here, which could be this or any other function. So this is the general form of the EM. So what we ended up doing is we went to the general EM, and now let's go back to the coins, use the general EM algorithm and see what alpha, p, and q would be for the coins example. So just to remind you, you toss coin 0 first, and if it's heads, I toss coin 1 4 times. If it's tails, I toss coin 2 4 times. I hide the toss of coin 0 and only show you the subsequent 4 tosses. And I do this multiple times. And so I get data that looks like this. Okay? So, and just a note about notation. Xi's are examples and Yi's are the corresponding tosses for coin 0. And the model, the first step in defining EM is to define the model. The model is a joint distribution, which I've written here, not this part. So the model is a joint distribution over xy in terms of your current parameters, and this is how we parameterize it. That's easy. So let's look at the EM algorithm. So what we need to define the algorithm is this step, the E step, and how to solve the maximization. The easy part is typically the E step, because all we need to do is estimate P of y given x, and we already have P of xy, so that's easy. But I'm going to introduce some notation in what might seem like unnecessarily complicating what's an easy task, but you'll thank me later. So we want to compute, the E step is computing probability of yi given xi and the current parameters. I'm going to define that whole term, the P of yi given xi and the current parameters, as CIH, is the probability that the yi for that particular example is heads, given the current parameters. And we know that it's proportional to the likelihood times the prior, and effectively, if you think about it, each example x can be seen as just a number of heads and number of tails. That's all we need. that's the sufficient statistics for estimating probabilities. So if the yi is right, so if this is, effectively using this expression, you can compute the value of p of yi given x, and I'm going to define that as CIH. And the reason I use the letter C is I want you to think of these as a count. Is this particular thing, if instead of a C, if I had a boolean, pretend that it was a boolean, is this thing a heads or a tails? And instead we have soft counts. This is 70% heads and 30% tails. So this is a fractional count. Probability of yi given x. So that is easy. So you can, there's some ugly math involved, but it's actually rather easy. You compute probability of CIH is this expression divided by the same thing for tails plus this for heads. So this divided by this plus this. Right? Yes.
Where did the current parameters go?
There I used the symbols alpha bar, p and q bar for current parameters.
I know where did they go, but did they transfer into these or not yet?
Where?
Starting from define CIH.
Right. Oh, everything is conditioned on the current parameters.
Oh.
Everything is conditioned on the current parameters. Yes. Questions? So what we have done here is simply to write down the math for probability that a particular example, the hidden value, is heads given the observation and the current parameters. And I should have mentioned this before. Let's pretend that I'm going to use the notation alpha bar, p bar and q bar for the current set of parameters. So that's the E step. So effectively we've estimated all the probabilities. These q's are now the c's. Okay, questions? And I encourage you to go over this again just to make sure that, well, let's say that just to make sure I've not made any mistakes in the slides. But, and also to convince yourself that you understand it. You may not necessarily get it the first time you see it, but you know, it's because there's so much math, there's so many symbols, and there's only so much time. The next step is the maximization step. So what we want is to solve for the parameters, maximize the expected log likelihood according to the expectation taken over the current set of parameters. So let's work out from the inside. First, the log likelihood. If your likelihood looks like this, the log likelihood is simply the log of that. Absolutely no shock there. So I'm going to get rid of this very quickly because seeing so many symbols makes me dizzy. So I just want you to know that this exists. The log likelihood can be written down in closed form given your xy, because this expression is completely a function of your model. Okay? So what we need next is the expected value of the log likelihood. So let's expand the expectation. Expectation is with respect to the q. Q is a distribution over y. So y can take either heads or tails. So this is just a sum of two things. Either the y probability of this being heads times this log of this, plus probability of y being tails times the log of this. But I've just defined this expression to be the CIH. And why did I do it? So that just to point out that these things are constants as far as theta is concerned. At this point, the C's are fixed. They're just numbers. When you're maximizing over this expression, the C's don't, they make no difference, or they don't change. You see that this is the expectation of the log likelihood. So we know how to write the log likelihood because that was just in the previous slide. It's one of these two lines here. When it heads, it's this thing. So it goes here, and when it stays, the other one goes there. Yes?
Were those parameters supposed to be the bar parameters? Or
There's nothing with a bar here. Notice that there's nothing with a bar.
So we've estimated parameters and now we're not using them to...
Aha, that's an excellent point. And in fact, this is a common cause for confusion with the n. Notice that the maximization is not with respect to theta t. Hold on, let's go back to the EM. You use theta t to estimate q. Once q is fixed, this is if you're maximizing this function, if you're maximizing over theta, this should be a function of theta, what comes inside of it. The only place where theta comes in is here. The current estimate is completely contained inside the q through this E step. So when you compute the log likelihoods inside the in this expression here, it's not using the current estimate, it's not using p bar, alpha bar, q bar, but they are variables that you are maximizing over. Those are the variables that you need to eventually take derivatives and do things. But yes, that's a good question, and in fact, those of you who didn't get that question, let me try to repeat it again so that when I write down the log likelihoods, notice that none of the alpha pq have a bar. Why? Because I want to maximize the alpha pq that have a bar are your current estimates of these values. You want to find the next estimate, and by definition this expression here does not have any superscript. It does not say that, it does not say expectation of y of log p x y given theta t. It's just with respect to some theta. And we want to maximize this function with respect to any theta. The current estimates are completely summarized inside this q because we use the current estimates to estimate this q, the CIH functions. Does that make sense? Questions? Yes?
So since theta t was used to produce those estimates, when we go to maximize theta, why does it not give you back exactly theta t?
Because you're maximizing a different function. So let's expand on that thought a bit. Why would you expect it to give you back theta?
I'm still trying to get where everything's coming from straight.
So there are two sets of parameters that you're constantly juggling. One is your current estimate. Your current estimate is just a set of numbers. They are fixed, they can't change. And then there are these symbolic thetas. You manipulate them, you maximize over all possible thetas, but the current estimate is fixed. The current estimate of the thetas is completely summarized as far as this maximization is concerned. It's summarized into the Q. Because you use the current estimate to get a value of the Q. Once you get the Q, you can throw away the theta t because they don't exist. They are going to disappear very quickly because they don't matter anymore. And then you write down the expected log likelihood using of this function, log likelihood, using any theta. But the expectation is taken with respect to Q, which is computed from the previous estimate. I encourage you to go back and maybe even implement the coins example. It's basically about 100 lines of code, and it is shocking how well it works. And it will also give you an idea for what are the different things that we are juggling at any point. So the punchline is rather simple. In fact, it's simple enough that it's a little disappointing after all this. We want to maximize this function with respect to theta. This is the expected log likelihood. We have all the pieces because we know the c's, they are fixed. And we know how to write this function, it's simply log of these things. So we need to find alpha, p and q, which is theta, by maximizing the summation over all I of this function, which I have written it here. Maximize over alpha, p, q, summation over all I of this horrendous function. And yes?
So you said we know the C's and they're fixed.
Yes.
Isn't C what we're trying? Well, so we don't know the labels, and C is the count of the labels.
C is a soft count. Your current
Your current
guess
Okay.
for what the label might be. But it's not a guess for the label, but it's a guess for the probability that the label is.
I guess I was confused when you said no. We know a guess.
We know a guess.
Okay.
Oh, okay, fine, sure.
That clear.
We have hallucinated a label using the current model. So once you get this function, this can be written in closed form because the log likelihoods can be written in closed form. So it's such a big function that I don't want to write it in a slide, or if someone asks me, I'll write it on the whiteboard. But you can take the derivative of this with respect to alpha, with respect to p and q, set them to 0, and get a closed form answer for the alpha, p, q in terms of the c's. In terms of the c's and these k's, because the k's are the ones that come from each example. Each example, in terms of number of heads that are in each example. So I did this, and you get a solution that looks like this. Alpha t plus 1 is simply the sum over CIH divided by number of examples. Pt plus 1 is something and Qt plus 1 is something else. Now, it's kind of boring if you just think of them as something and something else. The more interesting bit is the interpretation. If you had completely labeled data, suppose you had fully labeled data, you have x and y, what would alpha be? Alpha is the probability that coin 0 is heads. Probability that y is heads. How would you compute it?
Number of examples.
Exactly. Total number of heads divided by total number of examples. This is not the total number of heads, it's a soft count. CIH is the probability of getting heads for each example. If these probabilities were all peaked at 0 or 1, then this is the count. So what you're doing is, given the current model, estimating the next probability is simply effectively just counting, but not quite. You're maintaining soft counts. So P and Q have a similar sort of an interpretation, because this denominator here, because you're tossing coin, maybe coin 1 4 times for each example, the denominator is the total number of tosses of coin 1. And the numerator there is the total number of heads that coin 1 gets here. But not the hard count, but just it's weighted. These things exist in both heads and tails. They are like Schrodinger's cat. So we need to, each example will contribute to both. Questions? Yes?
So the 4 now is the size of the string.
Yeah, this is just for this particular example. In general, that if you take the derivative of that with respect to alpha pq, and I strongly encourage that you do this, because otherwise this might just look like a mysterious answer. So if you take the derivative of this with respect to alpha pq, because there is a 4 here, that 4 actually shows up from this. It's just for this model. So effectively, the probabilities of y given x and current model end up being treated as soft counts. If these probabilities were either zeros or ones, effectively these probabilities were indicator functions. Remember indicator functions when we were talking about naive Bayes? An indicator function is a function that says 0 or 1 based on whether its argument is true or false. So an indicator for heads would be summing over the indicator for heads would give you the number of heads. If these probabilities were indicator functions, then we are in the regime of fully observed data. Because we don't have observations, we propagate the uncertainty through the algorithm. But this is just one step. So this is just the m step for alpha t plus 1. Now you have alpha p q, these become the alpha bar, and you go back. You estimate the c's again, you go back to the alpha, and then you keep doing this till you're happy. So just to summarize this bit, you initialize the parameters randomly, you repeat, you alternate between the E and M steps till you're happy. The E step uses the current parameters to estimate the value of the distribution over the hidden variables. The M step uses this distribution over hidden variables to maximize the expected log likelihood. And very often, this is just for the 3 coins case, but very often the EM algorithm, typically you do this whole maximization step, you write down this thing and you write down about 8 pages of algebra, and you end up with updates that are often very intuitive, like this one here. Not always, but it ends up being intuitive. So I'll go through the example of naive Bayes just to point out, but last evening I was looking at this and like, maybe I should just implement this to see if it works. Because the math works, but how do you know if it works in practice? So I ended up writing the code. So and let's see if we have that. I'm going to run this a few times. Yeah. So I just picked some alpha, p, and q, and I generated 1,000 examples and ran EM for a few steps, and notice something interesting is happening. The alpha that I chose was 0.6. The alpha that ended up being estimated is roughly 0.35, 0.4, which is actually 1 minus alpha. Remember that there's no way of breaking symmetries. So what was P here ended up in the Q. What was Q here ended up in P. And alpha became 1 minus alpha. But this is just one run, so let's see if we can run it again. Same data, another random start, and this time it gets switched. Let's try again. It keeps switching between these two. So effectively there are 2 local maxima here. It's either this one or that one, and there's no way to break the symmetry. So yeah, the math works. Questions? Yes.
So it seems
Go ahead.
So it seems converge quite well. So the difference may be due to the adjacency inequality. I say that seems the convergence is very well, is very good.
What do you mean convergence is
well?
good?
Every time you get the same result.
Oh, I run it to 1,000 iterations, and you are guaranteed to converge to a local maximum.
Yes, yes. I mean the difference is due to
the difference is in initialization. So think about it this way, okay?
You said you do a random initialization?
I randomly initialize it. Think about it this way. Say I have a non-convex function that looks like this. This is, let's say I'm maximizing, so it's not concave. And this is not exactly what's going on in EM, but let's say I initialize at this point, and I climb the hill. I'll end up here. If I initialize at this point and I climb the hill, I'll end up here. If I initialize here, I'll end up here. So depending on where I initialize, I might end up on the wrong peak, on a different peak. But I'll always end up in one of 3 points. This and this.
Yes.
Right?
Yes. Well, I'm saying maybe, well, this is still approximation because you use the Jensen's inequality.
Oh no, the approximation, the fixing the Q to P of y given x theta actually makes this a tight lower bound. Yes. You had a question.
Yeah, I was just wondering, are those the true values up there that you've set, right? Or
Which one?
Is this how you set it up? The 3.EM alpha equals 0.6.
Right. Those are the true values that I set up, and these are, I generated some data once and keep running EM multiple times on it.
And you have random alphas, P's, and Q's again.
Yes, yes. Every initialization picks a random value for alpha PQ. Yeah.
So those are your actual values that you pass into the function?
The top line. Yeah. Questions? I encourage you to play with this. I encourage you to go back, work out the math, and actually maybe even implement it, mostly because A, it's easy, and B, when it works, it almost seems like magic. Because you hallucinate some labels, and suddenly you end up with the right parameters up to symmetry. Yes.
So does having more unlabeled data help your convergence at all, or like what is there any? Because you think that more data is always better, right?
Yes. So more unlabeled data actually helps you in different ways. It gets you better estimates for probabilities. So if I had run this using much less data, think about the law of large numbers. If you have more data points, your probability estimates get better. So yes, more data is good. More labeled data is, this is not a formal statement, but more labeled data is infinitely better. And the way to break symmetries is if I added just say 2 label points or 1 label point, that will let me disambiguate between which peak. Just 1 label point, right? So that all I needed here was one labeled point that will help me break the symmetry between these two. And you can play with that. In fact, you can initialize using your 1 labeled point, and that's it. You're done. You'll be in the right. Just you can the labeled point will put you in the right peak, right space, and then you get to the right correct region. Let's get back to the math. And in fact, the next bit I'm going to talk about is instantiating EM for naive base. Remember naive base, our good old friend. So, in fact, what we have right now, the 3-coin thing is actually very similar to naive base, in fact. But let's just work through this. How do you use EM for a setting that you've not seen before? For a new problem. In fact, for your homework, you're going to use it for a different joint distribution. So, and what I'm going to describe next, think of it as these are the steps in the recipe. First, you need to define the setting. You need your input and output. You need to specify what the x's and y's are. In all cases, EM is applicable when you don't have labeled data. So we have only points x. So the practical situation is you have a bunch of documents and you want to cluster them, and you have no way of you don't have any for whatever reason you don't have labeled data, and x's are the features, and just for now let's pretend that all the features are binary, the Boolean vectors, mostly because that makes the slides a little easier. The next thing that you need to do is to make an assumption about the model. In fact, that's the first thing you need to do. You need to define how your joint distribution is written down in terms of your in terms of any parameter. That will also tell you what your parameters are. So here I have assumed that you have a bunch of Bernoulli random variables, and this is the naive Bayes assumption. P of xy is probability of y times every feature is conditionally independent given the label. And we've seen this before. Just to introduce the notation, I'm going to use the symbol P for probability of y equals 1. And for each xj equals 1 given y equals 1, it's aj. Xj equals 1 given y equals 0, I'm going to call it P. Same symbols that we used before. And so, the parameters for this problem are all the P, xj and P, a, j and bj. P, a and b. So I can write probability, basically this whole thing gets conditioned on the theta. So that's the second step. So you write down how your joint distribution is parameterized in terms of your, in terms of whatever parameters you have. But remember, notice that I'm making a strong assumption here. I'm making an assumption that the data is generated in this way. And this is important. EM forces you to assume a certain model for your data. Now, what if your data is not generated according to that model? No guarantees. At that point, all bets are off. Same thing that we had for naive Bayes. If naive Bayes forces you to assume that your features are conditionally independent given the label, in practice, your features are most likely not conditionally independent given the label. So what can you do? You just hope it works. In practice, it may work, it may not work. You can't do much. But you need to make this assumption. You need some way to write down the joint. And then there's the E step. So the next thing that you need is the E step and the F step. The E step is easy. You need to compute Q of y, given your current estimate for the parameters, and I'm just calling it theta. Effectively, it's theta t. So Q of y is defined as probability of y given x theta. I can write probability of y equals 1 this way. This is easy. But I also know how to write down these two bits, because that's exactly what our model tells us. Right? So effectively, if I knew the thetas, I can on paper write down in code compute these values. The next step is the maximization step. So the next step is obviously the maximization, and I'm not going to work through the details because this is a lot of writing, but it builds character. Let's put it that way. So you should do it. So what you do is, and this is effectively a recipe for any EM. It's not just for naive Bayes. Notice that nothing here, except for the specific E, A, and B, nothing here says naive Bayes. The only place where naive Bayes comes in is in step 1, expanding this log likelihood according to your model. Right? So write down your log likelihood function on paper. You already have some estimate for Q, so write down the expected log likelihood like we just did. And the fun part, take the derivative with respect to every one of your every one of your parameters, set them to 0, and you get a new estimate for P, A, and B. Now, a lot of this is going to take at least a couple of in this whiteboard, at least 4 of these to write down. But does anyone want to take any guesses on what the P, A, and B will be? If you had fully observed data for naive Bayes, what was it? So let's say you have, your data looks like P is probability of how do you do it in naive Bayes? How do you calculate this?
Counts over 2.
What?
Counts of 1 by 2.
So it's sum over, this is the Iverson bracket. Remember the Iverson bracket? The indicator, x, no, not x, y. Right? And this is, let's say you have an example. So, does anyone want to take any guesses on what P will be at the end of this whole maximization step? Remember, in the coins case, we replaced the C, I, H ended up looking like counts, except they were not. They were soft counts. So what would you expect this to be?
Soft counts over n.
Exactly. So this part here, this is simply count of y equals 1. This is an indicator function that says 1 if y equals 1, 0 otherwise. So adding them all up is count. What we end up getting is P is soft counts. Simply just replace this with soft counts. And that's a pretty cool interpretation. Now, what is soft count? I've just written soft count. I mean, it means nothing if it's not defined. So, soft count of y equals 1 is simply the sum over the probability of y equals 1 according to your previous set of parameters. So, this is an intuitive explanation, and very often this, again, like I mentioned, this ends up happening quite often because you might, to convince yourself that you're right, you need to do the math. But in practice, the intuitive version, it ends up being what you expect it to be.
What prior did you put in theta?
It's basically uniform. They're all. I didn't put any prior on theta.
Well, no, it's still, even if you put uniform, you will get a Laplace.
Right. I didn't do any smoothing, basically.
Yeah, but the smaller, maybe it takes prior into account.
It could, if I wanted it to.
So
It could.
You should get a Laplace.
No, you won't actually, unless you explicitly try to put it in. So the numerator of this function here, I can derive it, but then it's going to make me write a lot. So let's take this. We can meet afterwards. But what ends up happening is just like in the naive base. So if you remember, when we derived the estimates for naive base, there was no Laplace.
Oh, that's different. Yeah.
Right? It's similar. It's actually very similar. If these P of y equals 1 given x theta t were actually indicator functions, if it was a probability distribution that was entirely peaked at 1 or 0, then you get counts, right? So it's pretend. So the other way of interpreting this is your fully labeled data is actually not fully labeled. Every example comes with a label y, but actually it's a distribution over y, which just happens to be peaked over whatever the label is. Does that make sense? And if you pretend that is the case, then the one step of EM will give you the answer. And if not, you iterate. If I had introduced priors into this, then those guys will show up as Laplace, but that would require it will be log of p, x, y, theta given hyperparameters, because then you're estimating more things. That makes sense? If I had introduced priors, they will end up looking like Laplace.
Yeah, they should.
They should, yes. And in fact, this is Bernoulli, so you'll introduce, the natural prior will be the beta distribution, and that will give you Laplace. So just to clarify this discussion, If you had fully labeled data, you'd just be using counts. There would basically no soft counts. So Aj is the number of times you see x equals 1 with y equals 1 divided by number of times you see y equals 1. If you work through the whole math of EM, the one update step, remember this is actually just one step inside the loop. You keep iterating this. Each step looks like this. We cannot count because we don't know the labels. But we have some uncertain estimates of the labels, so effectively we use fractional counts. And we define the soft count to be the sum of these fractional counts. And if you can, effectively this P of y equals 1 behaves like this Iverson function. Except it allows values between 0 and 1, not exactly 0 or 1. So let me wind up the discussion on EM. It's a general procedure for learning with hidden variables, and in fact most of the more sophisticated learning algorithms that involve latent variables, and these are the ones that show up all the time because labeled data is probably one of the most scarce resources we have, more than even printer ink. But most of these effectively look like a version of EM. They are variants. Sometimes instead of taking a fractional counts, you just pretend it's a complete assignment rather than just fractional assignments. That's called hard EM. We'll see that in the next class. And there's a pretty cool connection between hard EM and the k-means algorithm, which some of you might have seen. And the same idea applies for other models as well when you don't have labeled data. It's iterative, so you can't just do one step and hope it works. You need to keep doing it to convergence. And it's really important to remember that EM is not a single algorithm. EM is a recipe for building an algorithm. So given a new problem, you need to make an assumption about the model, and then write down the each step, work out the maximization, decide whether you can do the maximization analytically, or maybe decide whether you have to write define an algorithm for maximization. If you know an algorithm for maximization, for example, which is stochastic gradient ascent. If you ever needed to, you could use something like that, and you iterate. What we saw, the coins and the naive Bayes, are just instantiations of EM for when your random variables are all Bernoulli. But you could have, if you believe that your model is something else, then you can do you have to redirect the whole thing again. And your homework actually makes you work through this process when your random variables are Poisson. Just because you can. And a couple of practical things. This whole process is entirely dependent on your definition of the model. If your model is lousy, your results will be lousy. So there's no getting around that. So you need to think hard. There is no magic. I mean, that's the consistent lesson that keeps coming through in machine learning. There is no magic. You need to think hard about your problem and make some assumptions. And initialization is important, and the suggested strategy is probably the best one. You do random initializations, pick the one that has the highest objective value, and run with it. But in practice, it converges quite well. The next lecture, so I'm going to stop now, but just to give you a heads up, the next lecture I'm going to talk about some special cases of EM. In particular, you might have seen the k-means algorithm in a different class or in some other places. Turns out the k-means algorithm is actually an EM algorithm for a certain distribution, and it's a variant of EM called hard EM. I'll be around if there are questions. If not, free to go.